Welcome to section 3.4, absolute value equations and inequalities. So if you consult the notes on page 44 and 45, you'll see a couple of examples illustrating the types of problems that we're going to be solving in these sections. They rely on the sort of geometrical interpretation of the absolute value in terms of what it means for the numbers that we're looking at. So generally speaking, the absolute value of a number represents that number's distance from zero, its magnitude. So if we want to solve an equation along the lines of the absolute value of 3x plus 5 equals 17, there are two possibilities. Here we have an expression 3x plus 5. If we take that expression's absolute value, we get 17. So one possibility is that 3x plus 5 is equal to 17. So whatever that number is, if we take its absolute value, we get 17. One possibility is that number is in fact 17. That 17 has an absolute value of 17. The other possibility, and every problem in this section, or every equation in this section, is going to look something like this, generally speaking. The other possibility is that that expression 3x plus 5 is equal to negative 17. Right? If we take the absolute value of negative 17, we still get 17. So if 3x plus 5 is negative 17, then this equation would still be satisfied. So we are going to get two equations that we have to solve from most of these absolute value equations in this section. I'll begin by solving the first one. So if 3x plus 5 equals 17, I can subtract 5 from both sides. We see then that 3x equals 12. So dividing by 3, we see that x equals 4 is one possible solution. We'll come back to that. Let's solve the other equation first. If I subtract 5 here, I see that 3x is equal to negative 22. So x is equal to negative 22 thirds. So let's check that really quickly. I'll check the first one. Is the absolute value of 3 times 4 plus 5, well, that's equal to the absolute value of 12 plus 5, which is the absolute value of 17, which is 17. So we're good there. Our second possible solution, if we plug in negative 22 thirds, is the absolute value of 3 times negative 22 thirds plus 5. Well, that's equal to the absolute value of, we can cancel our 3's, negative 22 plus 5. Well, that's the absolute value of negative 17, which also gives us 17. So those two x values are our solutions. So our general strategy when we're solving these types of equations will be to write them as the absolute value of some expression equals some number. From there, we'll apply this concept, as you see in the note. Under definition 318, there are some different possibilities for what that number that our absolute value is equal to might be. Here in our first example, we had a positive number, and we have these two solution paths that we have to travel down. If our absolute value is equal to 0, for instance, if we were to solve the following equation, 1/4 absolute value of x minus 1 equals 0, we would begin by trying to write it in this form, the absolute value of something equals a number. Well, right now I have 1/4 times the absolute value equals 0. So I'll multiply both sides by 4 to cancel that 1/4. So on the left-hand side I have 4 times 1/4 times the absolute value of x minus 1. And on the right I have 0 times 4. So the 4 and the 1/4 cancel. I'm left with the absolute value of x minus 1. And on the right, I'm left with 0. So this is the second possibility. Here our absolute value is 0, and what that tells me is that this expression, or this number, what it represents, x minus 1, has a magnitude of 0. So we can think of this as saying x minus 1 is 0 units from 0. And if we solve the resulting equation by adding 1 to both sides, we see that x equals 1 is the only solution. Now you can check that by plugging that back in. The original equation, 1/4 times the absolute value of 1 minus 1, that's equal to 1/4 times the absolute value of 0, and the absolute value of 0 is 0. If we multiply that by a fourth, we still get 0. So our equation is satisfied, and x equals 1 is our solution. So whenever you have an absolute value expression equal to 0, the only possibility is that what's inside the absolute value is itself equal to 0. Now some absolute value equations will result in an expression along these lines. So if I say that the absolute value of some expression is equal to a negative number, we should interpret this as nonsense. This equation is not going to yield a solution, because no matter what I plug in for x, when I take the absolute value of it, I should get something greater than or equal to 0. I'm definitely never going to get negative 9 from taking the absolute value of something. So this negative means there is no solution. There is no way of taking the absolute value of even half of some x value and getting negative 9. The second topic in this section, the issue of the absolute value inequality, is treated on the next page of the notes, page 45. And again, what we want to use is the fact that the absolute value represents an expression or a number's distance from 0. So if I say that 2 times the absolute value of x plus 1 is less than 7, that would be equivalent to saying that the absolute value of x plus 1 is less than 7/2. So if I divide both sides of this by 2, I can get rid of that 2. Okay? So, how does that help me to figure out what x should be? Well, if this expression has a magnitude less than 7/2, that means that x plus 1 can be anything as long as it's less than 7/2 away from 0. On the number line, if we look at 0, go up to 2/2, 4/2, 6/2, 7/2, anything along that line could be our expression x plus 1. And in the other direction, negative 7/2. So any number in this interval has a magnitude less than 7/2, has an absolute value less than 7/2. So the resulting idea says that our expression x plus 1 is trapped by positive 7/2 on the high end and by negative 7/2 on the low end. And we can solve this chain of inequalities just like we would a single inequality. If I subtract 1 from each piece, I get negative 9/2 on the lower end, I get x in the middle, and I get, let's see, that would be 5/2 on the high end. So that is our solution for x. If we put that in terms of interval notation, we could go from negative 9/2 to 5/2, excluding those endpoints. That is our solution set. Now this is a little bit more difficult to check, but you could certainly give it a try. You can pick a bunch of x values from within this interval to plug back into your original inequality. It's not going to be exhaustive, you're not going to be able to check everything, but it will give you a pretty good idea of whether you're on the right track, especially if you check the endpoints. If you plug 5/2 in and negative 9/2 in, I think you'll find that those do not satisfy the inequality. So plugging those in will give us an idea of where the interval of the solution ends. So generally speaking, there in definition 319, whenever we have something along the lines of the absolute value of an expression is less than some number a, that means that the expression itself is trapped by negative a from below and by positive a from above, whenever a is positive. And the same will hold for absolute value inequalities involving a non-strict inequality. So the absolute value of an expression is less than or equal to a means that negative a is a lower bound and a is an upper bound whenever a is greater than 0. Here we see a slight adaptation of the absolute value inequality. We still like to get it in the into the form absolute value of something greater than or equal to some number. So if I divide both sides of this by 5, I will get my absolute value isolated. So the absolute value of negative 2x is greater than or equal to 2. So what does that mean? Well, it means that all of this stuff inside has to be at least 2 units away from 0. So on the number line, if we look at 0, and we go out to 1, 2, the location of this quantity x negative 2x can be anywhere here in the shaded regions. So one possibility is that negative 2x is less than or equal to negative 2. Okay, so that would be option 1. Option 2 is that that quantity negative 2x is greater than or equal to positive 2. So here we have our magnitude being larger than 2 because the expression itself lies to the left of negative 2. Here we have the magnitude being greater than or equal to 2 because the expression itself lies above positive 2. And then we need to solve the resulting inequalities. So if I divide both sides of this inequality by negative 2, my inequality sign will flip and we'll get x greater than or equal to 1. If I divide both sides of this inequality by negative 2, my inequality will flip and I see that x is less than or equal to negative 1. So those are my two possibilities for what x could be doing here. We have negative, shouldn't be negative there. I have 1 to infinity, and we are including 1 because the inequality is non-strict. And on the other hand, I have negative infinity up to negative 1. and that is my solution. Now, generally we like to write this in order from lowest to highest. So I might say from negative infinity up to negative 1, or from 1 to positive infinity. Now again, checking every single x value in either one of these intervals would take literally forever. But you can plug some of those x values in, plug in negative 3, negative 4, negative 2, negative 1, make sure they satisfy the inequality. And you can plug in some of the positive x values, 1, 2, 3, 25. Then you might check for the x values that aren't in this set. So if you wanted to check 0 or negative 1/2 or 1/2 or 0.9, you should not satisfy the inequality. So anything that's not in this interval should not satisfy the inequality, and everything that is in this interval should satisfy the inequality. And that is how we're going to be solving anything of this type, where we have our absolute value being greater than or equal to that value of a, in this case 10. Well, it ended up being 2 once we isolated the absolute value. So on page 45, bullet point 2 of that definition 319, solving the absolute value inequality, that details how we went about solving this particular inequality. So I'd just like to look at a couple more inequalities that are a little bit odd, and I do mean that in the sense that they're slightly strange. The first one, we see here the absolute value of 1/2 x is greater than negative 2. Now, we could go about solving this using the procedure illustrated in the definition, but that's probably going to get notationally a little bit messy. So I would like to think about what this is saying. This is asking us to figure out what x could possibly be where the absolute value of half of that number is greater than negative 2. Now recall that the absolute value of anything is positive, or I should say non-zero. So it really does not matter what we plug in for x. Whatever we plug in, it's definitely going to be greater than negative 2. So I would say that x could be any real number. And so our solution would be all real numbers, or negative infinity to infinity. And you can confirm that, perhaps not exhaustively, but you could plug in x values of your choosing. Any x value you plug in should satisfy that inequality. On the other hand, here we have the second inequality. In this last example I would like to look at, the absolute value of 1/2 times x is less than or equal to negative 2. Well, by similar reasoning, the absolute value of anything has to be non-negative. So if I ask for you to come up with something whose absolute value is less than a negative number, in theory I'm asking you to come up with something whose absolute value is negative, and there is no way of doing that. So these are both conceptually a little bit challenging. Well, maybe not challenging, but you do have to think of them in terms of what the absolute value really represents. So I kind of like these last two examples. They really get at the heart of what the absolute value does and how it relates the quantities on either side of our inequality. So that is all that I wanted to look at from this section. Go ahead and get started on those homework problems on WebAssign, and we will talk about any questions you have in class.